Yeah, thanks Jeremiah for the introduction. So I'm Mingyuan, and I'm going to talk about this work, Threshold Signature in the Multiverse. This is joint work with Leemon, Sanjam, Abhishek, Pratyay, Rohit, and Yinuo. So since this work is about threshold signature, let me give you a quick overview of what T out of N threshold signature is. So in threshold signature, we have N parties, each hold some secret key SKI. And whenever a message comes, parties can produce a partial signature using their private key, those sigma i's. And if you have enough partial signatures, you can aggregate them. In particular, if you have more than threshold many partial signatures, you can aggregate them into a succinct aggregated signature, which should verify under a succinct verification key. So the security guarantees that if the adversary corrupts less than threshold number of parties, then they shouldn't be able to forge a valid aggregate signature. So threshold signature is widely used in blockchain settings, and the standard way to do the threshold signature usually requires a distributed key generation setup. So you sample some verification key and a secret key from the underlying signature schemes. And this secret key SK is secret shared among all the N parties. So the SKI's private key from each party, they are correlated. And in particular, if you're using a Shamir secret sharing, they form a degree T-1 curve that interpolates the secret key SK. So the starting point of our work is that this starting model it may not be sufficient for some emerging applications. For example, when you set up a threshold signature on blockchain, you may not always want to do a threshold signature with all the parties. Maybe you trust some parties more than the others, and maybe they don't share the same interests with you. So in my example here, I have 3 out of 3 threshold signature with the left 3 parties, and then a 2 out of 4 threshold signature for the right 4 parties, let's say. And moreover, even for the same set of parties that you want to do a threshold signature, you might not want to do it with the same threshold. For example, if you have your high-stake message, you might want to have a guarantee that more parties have signed this message. Compared to a low-threshold message, maybe you're fine with only a small number of parties have signed it. So this motivates a new model where you have a number of universes, and each universe involves some specific subset of parties, and there's also a universe-specific threshold. And you want to do threshold signature within each such universe. Now, what does the existing solution, how can the existing solution solve this problem, right? So basically what you need to do is that you need to run a distributed key generation for each such universe. And this solution quickly runs into scalability issues as the universe grows. This is because, for example, if you look at Alice here, she's involved in all these 3 universes. And she has to hold a secret share for the secret key for each universe. So her secret state, or her secret keys, will grow with the number of universes that she's involved. And moreover, whenever she wants to, let's say, sign some message for a number of universes, then she has to sign this message, use each different secret share from those universes. So her secret keys signatures also grows. So as a crucial efficiency requirement for this primitive, we wanted the parties to have succinct secret keys. In particular, the secret key size shouldn't grow with the number of universes that a party is involved in. And moreover, whenever she signs a message, the signature should be reusable in all the universes that she's participating. So in a nutshell, the contribution to this paper is that we formally propose this primitive multiverse threshold signature. And then we give the first construction based on the popular BLS signature. And we provide implementation, and it's concretely efficient. So let me first say a bit, elaborate more on our model, some more details. So as I said, like the crucial efficiency is that the secret key for each party should be succinct, and also the partial signature should be short. Moreover, we require that the verification time and the aggregate signature should, just like a threshold signature, it should be a constant size. And also, things for each universe, you might need some interaction to set up a universe-specific verification key. We also require this interactive phase to be minimally interactive. In particular, for our construction, we only require one round non-interactive setup per universe. And we also consider the fully adaptive security against the fully adaptive adversaries. So usually in a single universe, when you consider fully adaptive security, the adversary can adaptively corrupt parties and query some partial signatures. In here, we also allow adversary to adaptively request some generation of universes. And even then, he shouldn't be able to forge a signature. And so I want to also mention that our correctness guarantee is also defined against malicious adversaries. So our scheme is robust against malicious adversaries. So okay, so now let me give you a quick overview of how we construct our scheme. So since our scheme is based on the BLS signature, so let me quickly recap what BLS is. So BLS is this elegant construction that uses a pairing-friendly group. So your secret key is just some random field element. The public key is G raised to SK. And whenever you sign a message, you just simply raise the hash of this message to your secret key. And the verifier verifies this equation by checking whether the hash of the message paired with the public key equals to the signature pairs with the generator or not. So usually the prior works who do threshold BLS, you based on the distributed key generation, do it in the following way, right? So in my example here, I use a threshold equals to T, so a Shamir secret sharing off is just a straight line. So every party gets some correlated secret key SKI that lies on the same line that interpolates SK. And whenever you want to produce a partial signature, you raise hash of a message to your SKI. And then to generate the aggregate signature, you can just do Lagrange interpolation on the exponent. So you take the group element sent by each party and raise it to the Lagrange coefficient lambda I, and that gives you hash of message raised to SK. So what we did in this paper is that we now allow party to pick its own SKI. So this avoids the distributed key generation setup, and this SKI will be the succinct compact secret key that this party will use across all universes. So now let's say I want to set up a universe for the first n parties, SK1 to SKn. So now since we don't have a DKG setup, their secret keys are not correlated. So if I want to look at the curve that interpolates all their SKIs, this might be a degree n-1 curve. And if I want to run the same aggregation strategy again, this means that I don't have a threshold version. I need n partial signatures to interpolate the aggregate secret key. So what we did is that in order to reduce this threshold from n to t, we're going to make use of the public points on this curve. In particular, the points on -1, -2 to n-t. So if you recall that the BLS signature, the signatures is a single underlying thing, the hash of message raised to F0, which is SK. Now we write this SK as an interpolation of n points, since this is a degree n-1 curve. Now this n points will consist of t points from the partial signatures and the n-t points from the public points. So our observation is that you can use the bilinearity of the pairing to move the power of the public points to the G. So basically, we break this one pairing into a product of two pairings, where you have the hash of message, the aggregated signature, which use T partial signatures. That's the aggregation on the left pairing thing. And also, we will use the aggregation of n-t public points. So this allows us to get correctness. And our signature will be those two double underlined group elements. So unfortunately, this scheme on itself is completely insecure, actually. So we need some additional, we designed a custom snarks to verify that the G to the public, this aggregation of the public point is well formed to avoid a forgery attack. And this is this step is the reason why we need a per universe setup to set up basically a verification key for the snark part. Now, an interesting point of this is that we also, even for a single universe, our solution actually provides an alternative approach for doing non-interactive distributed key generation. So yeah, so just to conclude, our paper proposed and constructed this primitive multiverse threshold signature, and I will refer you to our paper for the more detailed construction and security proof and the implementations. And finally, I just want to mention that we also have a follow-up work, which we call HINT, and it's already on ePrint. So this actually solved the multiverse threshold signature problem, actually have a better solution in terms of that this, this new scheme doesn't even require a per universe setup. So at day 0, each party sends some one-time message. And this allows for all future generation of new universes where party don't even need to send any additional message for setting up a verification key for each universe. And with that, I will end my talk here. Thank you.
All right, thanks. We have time for a few questions. Please come to the microphone.
Yeah, so if you go back to the slide where you say that you pick your own secret share keys.
Yeah.
So in that instance, sort of my one concern I have here is that if you have an adaptively malicious adversary in this scenario, yeah. What is stopping them from individually corrupting all of the, let's say, for example, half to the n parties, and for example, if you choose if you let parties choose all of the same SK1 through n/2. That would reduce the degree of the polynomial potentially under T. Is there anything that sort of prevents that sort of attack in this scenario?
I'm not sure I understand. Are you talking about a rogue key attack, or? I'm
not certain. I just.
So basically, even if you adaptively corrupt some number of parties, as long as the if you corrupt less than the threshold, then the sum of the public points, which is n minus t, plus some number that is less than t,
right,
is still smaller than n, which doesn't give you enough information to interpolate the entire curve, so that's why you cannot generate forward.
Oh, I see. Thank you.
Yeah.
Hi, yeah. Thanks for the talk. I had a question about the threat model you use. So do you allow the adversary to corrupt the same numbers of parties across all universes, or can the adversary corrupt different set of parties in each universe?
Right, so each universe can have the same number of parties. So universe can have arbitrary subset of parties and a threshold. You can define it arbitrarily. We don't require the subset to be different or anything. There's no restriction. You can even set up a universe, two universes that has same subset of parties, same threshold. Even then, it's fine.
And is the adversary allowed to corrupt the same, like different sets of parties in each different universe, or are they restricted to kind of using a set for each?
So as long as within, so when you do a forgery attack, you forge a signature under some universe. As long as in that universe you corrupt less than the threshold number of parties, then you cannot forge a signature.
Thanks.
Yeah.
All right. So I guess one quick question. You mentioned the, I guess, newer version of the scheme.
Yeah.
How does the concrete efficiency compare when you?
Right. So the concretely, first of all, the signature size compared to this work is slightly larger, and the concrete efficiency is maybe 2 times, or I'm not sure, a small constant overhead compared to this thing. But the new scheme doesn't. For example, here you still need a per universe setup, and even this one-round setup, you need to know the public key of all the parties. The new scheme is completely silent in the sense that you just generate your own thing and publish it, and that's it. Yeah.
Okay.
So there's a trade-off between efficiency and the interactions.
Okay. Thanks. Yeah. All right. Let's thank our speaker.